Welcome back to the Chem OG. Today we're going to talk about degrees of unsaturation. And when we talk about saturation as a word, saturation means that we're giving something and taking it to its full capacity. And so if you have a saturated market, let's say in business, that means that there's so much of that product in the market that anybody who wants to sell some more can't because nobody wants to buy it anymore. The market's saturated. Or let's say that you're pulling an all-nighter and after a long night of studying, you're just like, you know what? I'm reading this and I don't understand it anymore. So my brain is saturated. It can't take on any more information. I need to go to sleep. And so saturation means filling something up to its capacity. Now, when it comes to organic molecules, saturation refers to the following. A saturated molecule is the one that has the maximum number of attached atoms. And so before we talk about what it means to have the maximum possible, let's actually take a look at the opposite. Let's take a look at what are the things that can limit the number of attached atoms. So there are two things. The first one is a ring. So if I take a look at a 5-carbon chain, so we're looking at N-pentane here. If I take those 5 carbons and I form a ring with them, check out what happens. So originally, when I take a look at pentane, pentane has 5 carbons and it's got 12 hydrogens, if we count up all the hydrogens. But if I form a ring, I found out that my number of hydrogens went down. It went from 12 to 10. Okay? So when I form a ring, what ends up happening is that I take out 2 hydrogen atoms. So anytime you form a ring, that's going to take out 2 atoms in the process of that ring formation. The other thing that can take away atoms is the following. Pi bond. So let's take that pentane again, and let's introduce a pi bond to our molecule. So originally our molecular formula is C5H12, but if I introduce a pi bond to our molecule, let's say at carbon number 2, what's going to happen is when I count up my hydrogens, I will find out that there are only 10. Now, if I add another pi bond between those same carbons and introduce a triple bond, I take out another 2 hydrogen atoms. So now I have C5H8. So a pi bond also takes away 2 atoms. And just to make sure we got this, a double bond, remember, is 1 pi bond, and a triple bond is 2 pi bonds. So that's why the triple bond was able to take out 2 atoms. So those are the 2 things that can limit the number of possible atoms that we can have on our molecule, a pi bond or a ring. Now, every time we introduce a ring or a pi bond, right, we're going to take out those 2 atoms. So the total number of rings and pi bonds is known as the degrees of unsaturation, and that is our topic of the day today. Sometimes this is called double bond equivalence. So you may see DBE for short or DoU for short. Both of these are the same exact concept. So essentially our number of degrees of unsaturation is going to depend on the following. Because the number of rings and the number of pi bonds is half of the number of atoms that are taken away. Or in other words, every time I put in a ring and every time I put a pi bond, that takes 2 atoms away. Then the number of degrees of unsaturation, if I'm interested in knowing how many rings and how many pi bonds I have altogether, I'm going to take a look at what the theoretical maximum number of atoms is. And I'm going to subtract from that the actual atoms that are on the molecule. And I'm going to divide that number by 2 in order to figure out how many rings and how many pi bonds I have. Because remember, each ring and each pi bond takes away 2 atoms every time that happens. So, all right, how do we count that maximum number of atoms? Because there are 2 numbers in that formula that I just gave you, the maximum number and the actual number. How do we count the maximum number of atoms? Well, if I take a look at that pentane, I notice that every single carbon is attached to 2 atoms, at the very least. The ones that are not attached to 2 non-carbon atoms are this carbon right here and this carbon right there. Okay, so if I take a look at the number of atoms that are not carbon, right, the hydrogens that are on this molecule, that number of hydrogens is, if I'm looking at for a general formula, every single one of these carbons has 2 hydrogens attached to it, except the ones at the edges. They have an additional 1 each. And so that means that my maximum number of atoms, if I'm looking at the hydrogens on this molecule, it's going to equal twice the number of carbons because each carbon has at least 2 hydrogens, plus an additional 2 for the carbons at the ends. Okay, so when we have only carbons and hydrogens, our maximum number of atoms is going to be 2 times the number of carbons plus 2. What about atoms besides hydrogen? Because certainly organic molecules aren't completely exclusively constrained to carbons and hydrogens. So let's take a look at an example molecule here. And what I did was I inserted in the place of some of the hydrogens, certain other molecules. So for example, I put a chlorine here and a bromine here and an oxygen there and a nitrogen there. And what I wanted to see was what was the effect of adding each of these guys? Well, when I added the chlorine and the bromine, essentially what those two did was they took the place of one hydrogen. Okay, so the halogens just simply replace hydrogen. So that didn't really affect the number of possible atoms that I had. For each hydrogen that I took away, I added exactly one halogen. So the halogens just simply replaced the hydrogens. If I take a look at the oxygen that I added, even though the oxygen took that hydrogen's place, you could still see that there's a hydrogen attached to that oxygen. So oxygen doesn't really have an effect. Okay. And the same thing is going to go for anything that's in the same column as oxygen. So sulfur, for example, has that same effect where it's not really going to affect the number of atoms that we have. Even though the oxygen took the place of a hydrogen, there's still a hydrogen attached to the oxygen. So the maximum number of hydrogens is still maintained. And if I take a look at what the nitrogen did, well, there used to be one hydrogen here. Now that nitrogen, by attaching it, it allowed me to add an additional hydrogen. So at this particular spot, at this bond next to carbon, instead of having just one hydrogen, now I have 2. So every time you add a nitrogen, that adds an extra hydrogen to the mix. And so for piecing all those things together, right, halogens simply replace hydrogens, oxygen has no effect, and nitrogen adds an additional hydrogen, then my actual number of atoms that I'm worried about are the hydrogens and the X, and X here represents halogens. So a lot of times in organic chemistry, when we put down capital X, it means that we're looking at the number of halogens. And my maximum number of atoms that I had from the previous slide is something I need to adjust. So we said it was 2 times the number of carbons plus 2, but now we need to add the number of nitrogens on my molecule because each nitrogen now adds a hydrogen. So now we're going to take those two things together. We have the actual number of atoms, we have the theoretical maximum number of atoms, and our degrees of unsaturation is going to be the maximum number of atoms minus the actual divided by 2. And so if I put that together, here's what I get. The maximum number of atoms is 2 times carbon plus 2 plus nitrogen, a number of nitrogens, and the actual atoms is going to be the hydrogens plus the halogens. So that's a really clunky equation. So to simplify, here's what happens, right? If you do the algebra and you divide by 2, the formula simply condenses down to carbons plus 1 minus x over 2. And I'm using this variable x here as a stand-in for the hydrogens plus the halogens minus the nitrogens. So the first step you should do when you take a look at the molecular formula is take a look at how many hydrogens you have in that molecule, add the halogens, subtract the nitrogens, and then take that number divided by 2 and plug it into this equation. So carbons plus 1 minus this whole aggregate value here and divide by 2. Okay, so let's take a look at a couple of examples. So let's say I got this structure. So here's what I'm going to do. Let me figure out the molecular formula. So I got carbon, carbon, 1, 2, 3, 4, 5, and then there's a 6th carbon out here. Don't forget that. And then I'm also going to take a look at the number. Wait, hold on. Anytime you have an actual structure in front of you, please do not use this formula. It's not a good use of your time. The best use of your time is simply, instead of trying to find the number of carbons, the number of hydrogens, and whatever else happens to be on that molecule, and using this formula, dude, just take a look at that structure, count up the number of rings, and count up the number of pi bonds, and you'll get the same exact result. So whenever you're provided with a structure, instead of the molecular formula, just simply count up how many pi bonds and how many rings you have. So if I take a look at that structure, I have 3 pi bonds, and I have 1 ring. So that is 4 degrees of unsaturation. And I guarantee you that if you take a moment and you count up the number of carbons, 6, and the number of hydrogens, also 6, and you plug it into this formula above, you will get the same exact result. So spare yourself the trouble, count up how many rings and how many pi bonds you have in a structure. All right, so here's our formula one more time. Let's take a look at another example molecule. So let's say I have this one. All right, so what do I got? I got 1, 2, 3, 6 carbons in this ring, and I have 1 carbon in here, and so that's going to give me 7 carbons. No, wait, don't do that. Take a look at your structure and just count up pi bonds and rings. That's all you got to do. And so I have 2 rings in the structure, and I have 4 pi bonds, 3 in this ring and 1 in this ring. So that's going to give me 6 degrees of unsaturation, 2 rings and 4 pi bonds. No reason for you to be able to figure out the molecular formula. Unnecessary use of your time. All right, so let's take a look at an actual chemical formula and try to figure things out from there. So let's say I have C9H8O4. So well, the first thing you should try to do is you should try to calculate this variable x. Now, in terms of halogens, hydrogens, and nitrogens, I really only have hydrogens here. So x is going to be 8. So my degrees of unsaturation is C plus 1 minus x over 2. So C plus 1 minus 8 over 2. So that's 9 plus 1 minus 4. The number of carbons is 9, as you can see the molecular formula. And so I'm going to have 10 minus 4, which is 6. So this structure is going to have 6 degrees of unsaturation. All right, let's do one more. So let's say I have C9H10N5O4Cl. All right, let's incorporate everything we just mentioned. So the first thing I'm going to calculate is how many hydrogens plus halogens minus nitrogens do I have? So my number of hydrogens is 10, my number of halogens is 1 because there's a chlorine, and my number of nitrogens is 5, so that x value is going to be 6. So now I'm going to plug that into C plus 1 minus x over 2. C plus 1 minus 6 over 2 is going to be, in this case, 9 carbons, so I have plus 1 minus 3. And 9 plus 1 minus 3 is going to give me 7. So there's 6 degrees of unsaturation on this molecule. Thank you so much for watching today's video. Please help to support this channel by hitting the like button. And if you haven't done so yet, please hit subscribe.